So welcome everybody to the next seminar in the DSA Seminar Series. Today we're delighted to have Steph Locke with us, and she's a data scientist and CEO of Nightingale and Locke Data. And the mission statement, I guess, of Nightingale HQ is to help manufacturers innovate through AI. And today she's going to be telling us a little bit about reproducibility in machine learning and AI. So without further ado, I'll hand over to you now, Stephanie.
Good afternoon, everyone. Thank you for coming along today. So we have about half an hour. The goal is I'll talk for maybe 15 minutes, maybe 20 on reproducible machine learning, and that leaves us plenty of time to go into more specifics. So you'll have plenty of time to ask questions. Now, the reason why I wanted to talk about reproducible machine learning is partly because I love to know I'm right, and partly because problems happen all the time. So even when you're doing all sorts of things right, having the way to restart your work without having to recode it, run all the different bits, and worry about getting the wrong outcome, working in a reproducible way really helps give you that level of certainty. And that's important in a business context and in an academic context. So a little bit about me before we get going. I'm a data scientist by trade. I've been doing data science now since about 2013 across industries like financial services, cybersecurity, insurance, utilities. I've even helped people who train horses for races for a living. So I focus on how we meet business challenges and help translate that into real world solutions for people. So I spend a lot more time on the practical side. I can describe and teach you how regressions and ordinary least squares works and gradient descent works, but I'm much more focused on the implication rather than the maths behind it. I've been a big advocate of the technical and data communities locally in Cardiff for coming up 10 years now. So there's user groups and conferences and things locally that I've set up, all with the goal really of helping more people learn and enjoy what they do, and having a great network of people who understand what you do for a living rather than everybody thinking I fix printers. So you can join my network. I'm on Twitter, I'm on LinkedIn, you can email me. I regularly mentor people as well. So if you're interested in careers advice and things like that, you can connect with me and we can sort that out. And also, we're running one of the thesis projects this year. So if you're interested in natural language processing over business project briefs to try and identify requirements, register your interest and we'll be working on that project this summer. So today I'm going to talk about reproducibility, what the benefits of it are for you and other people, and then go into some of the high-level recommendations. I'm not going to do this as an end-to-end technical piece, in big part because it really varies by situation. It varies as to the technologies that you might use, vary whether you're using R, Scala, Python, Julia. So I'm keeping it at the high level, but giving you some recommendations as to where you can go to get the detail for your specific use case. So I've been talking about reproducibility, but it's important to define what it is and also give you a framework for how you can be working out whether it is useful to go to full reproducibility or somewhere on the spectrum. So you can think of, we've got two parts as data scientists and AI engineers. We have the data that we use to train models, and we have the code that we use to actually do that training. Data is inherently very complex. You can have the same code, run it over different data, and have a different outcome. Similarly, if we don't if we use a different algorithm, we get a different model. So there's a lot of complexity inside the analysis and data science part of reproducibility of our code. It's not a deterministic process inherently because of that data. So the goal, we have levels of ability to be able to get the same outcome or similar outcomes based on whether your data and your code stays the same. So if you build a model that says, for instance, with micro mobility, bike sharing schemes, things like that, that train stations, coffee shops, and schools are the most significant predictors of utilization of shared bikes, and you do that inside with different models, and you do it with data sets from different cities, your work is generalizable. So the model that you build holds across multiple situations. If you use the same data and get different and use different models and coding pipelines and get that same conclusion, it's robust. It means that we're able to get the same conclusion in multiple different ways. So it's less likely to be an artifact of your specific model generation process. On the flip side of that, if your code is the same, but you pass through different training sets, so you take a data set from the beginning of the year and a data set from the end of the year, and they end up with the same rough model, then your results are replicable. It's closer to holding true over time or different places. Reproducibility is about taking the data and the analysis that you've done and making sure you get the same outcome every time. So this is important because this is usually a starting point for somebody to be able to evaluate your work, for you to be able to run it again and again. If you can be confident that your results if you can be confident that your results is stable, this allows you to start testing and trusting your work more safely. So with reproducibility, it's all about taking the initial same training data set and the code that produces a model and being able to get the exact answer again and again. So no matter who runs it, they get the same results. That means we have to have the same environment. If you're running with different packages in Python or R, and though you need to be able to specify those and exactly what version you used, because of course things change over time. People might fix bugs, they might introduce bugs, they deprecate code. So we need to be able to have the same setup to begin with. We need the same data, so we can't just, it isn't reproducible if we're always using the latest month's data. And the code shouldn't need changing to be run. So that means no hard-coded references to files on your C drive inside your named directory. It's got to be able to work as is without modification. And the goal really is about producing the exactly same results. No rounding errors, no error messages, same results, same charts every time. And that is really tough, and we'll look into, but this gives you that really strong starting point for being able to have this process scaled out. So lots of people or lots of machines running the same process. It allows you to go through auditing. It allows you to run it in a continuous integration and deployment environment. It allows you to document it more safely. It allows people to troubleshoot it, identify areas of improvement, and so on. But robust, repeatable, and generalizable might also be goals that you could aim for along the way, or instead of, because you might be interested in understanding the causal implication, the causal piece. So you might run different models to see how sensitive they are to the training data. You might be interested in making sure that your code can run on different data sets so that it can run over time. So really, reproducibility is a good thing, but robust and repeatable and generalizable are also useful terms and goals to have in mind as well. There are tons of benefits to this. So for you, working on making your code and your analysis reproducible from the beginning gives you fewer problems with the portability of your code. So I don't know about you yet, if you've already gone through this, but things like Python virtual environments, Docker containers, and other things, you start off with downloading all the packages on your machine, you start doing something cool, you leave it for a month, you come back and you've run a bunch of like updates, and now your code works slightly differently. By working on making sure that your environment is specified and you're able to use it from scratch, you're able to use that environment every time, you get less code maintenance that you have to do, less troubleshooting about why things don't work now. You have to, you'll be less sensitive to things like function deprecation, changes in behaviors in upstream dependencies. It gives people a clear standard to work to. So inside a lot of production environments, you'll often see we use this Python version and these different levels of these packages in our production environments because we know they work, and this is our baseline for all our code. By having that level of standard, it makes it much easier to enable everybody to collaborate on the same code base and make it easier to put things into production then. So you're not having to manage lots of different versions Or if you do have to have those different code version, package dependency versions, it's all bundled up in an easy to use way. So being able to make things reproducible from scratch makes your life a lot easier over time, and particularly when it comes to taking what you've built and getting it into production. It isn't just about you, though, as much as your experience writing code and building models and everything matters. But it really matters to stakeholders. So what we're doing right now with data science and AI is very similar to the Arthur C. Clarke quote of any sufficiently advanced science is indistinguishable from magic. We're often doing what appears to be magic. And people do not like unstable results. So if you're producing consistent answers, that greatly increases people's comfort. And interestingly, I found it is much better, people much prefer it if you're consistently wrong rather than inconsistently right. So the stability of your outcomes actually helps people feel more comfortable. Having the ability to say, this is the data I used, this is the code environment I used, here's the code, and now you can go and get the results, helps with auditing. So if you work in a regulated industry like financial services, healthcare, things like that, if you're making models that impact people or your business, quite often they have to go through a third-party audit or even approval from a regulator. And if they have to have just a paper that says, here's the results of my model, trust me, it's good, then you're going to have a much tougher time in getting that model signed off. But if somebody can run it, make sure it works, step through the code, it becomes a lot easier for somebody to sign off that you knew what you're doing, you took the appropriate actions, and you led, and your code led to a reasonable outcome. Your code being reproducible and being able to rerun in different in the same environment and make that environment easy makes your code more maintainable. So one of the things that we need to be careful of, and I have to be careful of this particularly as a CEO of a startup, is it's very difficult if people are irreplaceable. If somebody gets ill, if somebody moves on to a new job, if somebody doesn't look at the code for 6 months, if the work isn't reproducible, if it can't just run when freshly downloaded and be able to get the date, like the latest data, or it might be repeatable, then that model actually becomes junk. If people can't work with it easily and it's a black box that nobody can touch, nobody can fix, nobody can upgrade, nobody can extend, that is a huge business risk. So working hard to make our code work against data in a reproducible way helps us ensure ongoing value and sustainability of our work. And that is something that is going to be really crucial to data science and AI over the next 10, 20, 50 years. Because if some of you have seen that, like in R and even in Python and stuff, there is still Fortran code from the 70s written and embedded in how we construct models. There's banks using machines from the 80s and beyond with 150 years of data. our stuff has to run for far, far longer than we would expect. So maintainability and the ability to get the code running, check the outcomes, and be able to make changes if needed is really important. And we have an easier time operationalizing our models, getting them into production. And when we have that quicker time to take a model from training to something like an API or a batch scoring process, that means we get value out of that model far sooner, and it costs us much less to get it into much less investment to get that model. So we earn more money, sooner. So if any of you have done finance, our net present value of the investment and the return on it is much more substantial because of it. So businesses want you to quickly get code into production that is maintainable, that has consistent results, and meets all of their compliance requirements. It's good to code these things safely and reproducibly. So let's talk some of the recommendations, because it's all great saying reproducibility is wonderful, but you have to get the right data and you have to get your code working consistently, and you got to get your environments right. It's actually quite a tough task to aim for reproducible. One thing to start thinking about is your data and the acronym FAIR. Is your data findable, accessible, interoperable, and reusable? So this is an increasingly used acronym and approach inside academia that we can also apply in industry. So the data set, getting that the same, how are you going to find it? All the weird columns and funny jargon names and things like that, what do they mean? So you need what's called a data dictionary, usually as a starting point. What does everything mean? What are the measurements? What are the units and things like that? How is your data going to be accessible? Like, is it always going to be via an API? Is it via a database? What happens if these things go down? How do you know you're getting the exact same data as you did? What kind of versioning processes are sitting on it? And then finally, do you actually have the rights to use that data? One of the common issues I see is that many businesses will collect customer data, and it'll be specified for the purposes of, performing transactions for the customers, and maybe a standard clause to support statistical analysis of business operations. If you use that customer data to build a model that predicts whether they're going to leave the whether you're going to churn to a new to one of your competitors, do you have the rights to use their data to produce that model? Does that actually count as the statistical analysis piece? What if you start using it to apply the results to other people, other customers? Have you breached your contract with that customer? So you need to be careful. And you also, if you're going to share your data to make it for an audit and things like that, again, can you legitimately use the data that way? If you use open data to supplement your internal data, do you have the rights to use it for commercial purposes, for instance? So you can go through FAIR, and gives you quite a nice checklist to help you make sure that the data part of your process is at least reusable so that you can make your code reproducible. When we're building our models, it's really important you start logging what happens. Log the code you ran, log the hyperparameters, log everything. Log all the things. Get using version control. If you're not used to GitHub, you need to be. Source control is a vital skill that really everyone in technology needs, especially data scientists. You often need to think about how you're going to fix your random number generator. So quite often, for instance, if you do clustering, you get your data, you say if you're doing like k-means, you say you want like 10 clusters. It will initialize 10 random points inside your data and start going through iterations to build those clusters. That means unless you fix the random number generator by fixing the seed to say, always use this starting value, it could generate 10 different clusters, cluster starting points every time, and you might end up with different customer groupings based on that initialization. So you need to be thinking about how we have randomness inside our algorithms to make sure that you account for it over time, and track your dependencies. Whether it's a Python environment variable, using a Docker container, taking a checkpoint or a snapshot of your packages and things like that, track your dependencies. Because those things, that upstream change is a really significant risk to your code reproducibility. There's tons around what's called ML ops, machine learning operations, that can help us work on building reproducible data and machine learning pipelines. And there's a few that I'm just going to highlight here, but the link and you'll get the slides. These take you to a big, huge list of ML ops capabilities. ML Flow is an Apache project that sits in things like Databricks that allows you to log data, experiments, and register outcomes. Drake is a really great package in the R world that for building reproducible end-to-end analysis, and has checkpointing and caching. So instead of having to rerun the whole thing at different times, you can just, for long-running operations, you can cache it to a certain point and then run the latest bits. Azure Machine Learning is a cloud service for registering data, experiments, data sets, and going on to host models, interoperable with ML Flow, and that's really useful for reproducibility. And also includes some of this as well, Fair ML. One of the things that you're going to want to do when you build your models, depending on the complexity or the sensitivity of the use case, is you're going to want to start putting explainability and fairness checks and monitoring processes in place as well. So FairML is a Python package that can be used to help you assess whether the outcomes that your model delivers are fair to one of like 5 definitions of fairness, different groups inside your data. So there's lots of different ways that you can be making your code reproducible, but you need to be logging, you need to be getting version control, stuff like containers and things like that helps. And there's tons of different frameworks that you can use that will help make your life easier to save you having to code everything from scratch yourself. So that's reproducibility. That took me longer than I thought. I've got plenty of time for questions personally, So thank you. You can follow up with me on email as well. I really appreciate your time today.
Okay. Thanks, Stephanie, for a very interesting talk. Has anybody got any questions? So I've got a couple. So if you're using, okay, so let's say your goal is to do some data analysis, machine learning, which is reproducible. Do you think it's easier to achieve that goal if you're using a cloud solution or if you're using, let's say, just a local solution?
It depends, because it depends on how much control you have over that cloud environment. So if you use a platform as a service type of solution, things like with databases and stuff, they'll be doing upgrades and things behind the scenes. So there might end up like a change to fix a bug that you will have no control over because you're taking the platform. If you're able to say, I want this version and this version, then you can have a lot of control. So for instance, in the Azure ML environment, it has a number of default environments. They don't do that. There'll be like a latest, which is always getting the bug fixes and things like that. But you can always say, I want this environment as at the packages from this date. And that gives you a lot of control.
So would you say reproducibility is a software issue, or is it a hardware issue as well? So if you run the same algorithm on different hardware, does it generally give you different results?
There is a small risk, and depending on the on your solution, that small risk or small floating point differences on your hardware can matter. So some of it's not too bad with CPU-based calculations because we've been running algorithms on CPUs for a long time, so there's a lot of standardization. If you start doing kind of CUDA-based distributed calculations across different clusters of machines with different GPUs and things like that, you do start encountering that risk of variability from hardware. One thing we've also seen a lot is things like chart production, and so if you're producing things like your documentation and your outcomes and your reports and your papers and stuff from in a reproducible environment, actually sometimes Linux and Windows have different drivers and end up producing not quite the same at a pixel level images. So you can get ultimately something that looks the same but isn't fully reproducible across operating systems.
And you mentioned MLOps. So a lot of students might be familiar with DevOps. So how does MLOps, how does that differ from DevOps?
So DevOps is both a principle and a practice and tools these days. So the principle really of DevOps is about reducing the bottlenecks in the development and maintenance and kind of productionization of code. So developers take on the responsibility of things like writing unit tests for their code. They use continuous integration and deployment environments to streamline the operationalization process, the testing process, and things like that. So we have a lot of DevOps tools that are born out of the principles of DevOps. The MLOps tools that we're seeing, and there's a huge system of them, are essentially the data science specific tooling to support DevOps as a principle. So getting things into production sooner, getting it into production with greater quality, making it easier for people to interoperate and communicate about the results. ML Ops spends a lot of time. It is the technology that we use to make DevOps in data science happen.
Yeah, so you mentioned quite a bit about, reproducibility is concerned with when you run code, it gives you the same result. But when you're running a data science algorithm, the result is a function of the data. So is there reproducibility around how we capture data or how we generate data? Is that a different topic, or does that fall under the umbrella of machine learning reproducibility, or is that something else?
Yeah, so there's a couple of things that in there. We very rarely have control over how data is captured. So we cannot usually control that part of the process. What we can usually control is once the data is ingested into the data warehouse or the database or produces a flat file extract, we then have control over it from there. So then it's useful to have processes that make sure that things like change it, updates to the data, whether that could be something like a correction, somebody implementing their right to be forgotten, or a system correction, things like that. We need to be able to understand the process that happens and how that's going to impact our overall reproducibility. So you might say, I'm going to take this data as it was on this date, and I'm not going to allow any corrections or updates to it. That's one way to fix the data, to basically snapshot it to get yourself reproducibility. Practically, though, you might need to accept fixes to the data, corrections and things. And that's where version control comes in.
Okay, so Paul has put a question in the chat. How do you get ML developers to buy into making their code reproducible? In my experience, developers often seem enthusiastic to design cool things, but less enthusiastic to document them.
Yeah, I've definitely seen that. I start out with a lot of self-interest. So if we don't document things and we just go for the coolness factor, in the real world, it's us 6 months down the line after doing 2 other projects who have to come back and support that work that we did. So anytime we cut corners, anytime we don't focus on quality or documentation or strong communication, we are making life harder for ourselves in the future.
Yeah, I think a lot of communities do try to incentivize reproducibility. I know in the research community, there's a huge emphasis put on making code available on GitHub, and then it leads to so other people can use your code and cite it. So I think we're starting to come around to that as a community, the machine learning community in general. Like I think if you most machine learning projects generally come with a GitHub repository that you can download the code. I know just making the code available isn't exactly reproducibility, but it goes a long way towards that goal.
Open science is and at least just publishing your code is a great step forward.
Are there any other questions from students? So maybe you could talk about some of the companies you're working with, or some of the products and services that your organization is involved in.
So at the moment, I actually don't personally do a lot of data science by hand anymore. one of the things that we're focusing on at Nightingale HQ is helping businesses and manufacturers specifically who are typically they have varying technology savvy levels, particularly in the operational tech. So like you've probably seen the GIFs of the machines that like chuck out the unripe tomatoes and stuff like that, and they're working super fast. So they have this great operation, this like hardware technology, but they're still very much adopting information technology and SaaS cloud products and things like that. So what we're actually trying to do quite often is use some of the off-the-shelf available tools to lower the cost for them to start building AI and data science into their capabilities. So we're looking at things like Microsoft's Form Recognizer API. With Form Recognizer, it has pre-built computer vision models that like extract invoice data, ID document data, things like that. But we're also able to train it up to extract key information from things like health and safety forms and bring that into the database. So it requires like 30 documents to start training that custom model. And you can then get an API and start getting value. So we're doing that with a wide range of organizations, really just helping lower the cost of using data science and using AI so that when somebody as a data scientist comes in, they're equipped with the tools to solve the easy problems, and then they're able to spend more time focused on the like higher value challenges that require bespoke solutions. I'm hopefully going to be doing a cool project around identifying underserved geographical areas for public transport to help work out where people should invest some of their public transport spending and things like that, and actually get hands-on again with building models from scratch.
Sounds good. Yeah, in trying to improve connectivity, I guess, in the city and so on and so forth. Yes, it sounds very, very, very useful project to be involved with. Are there any further questions from anybody? If not, we can bring the session to an end. So thanks again, Stephanie, for giving a very interesting talk.
Yeah,
and,
thank you, Steph.
And as Stephanie mentioned, she's got an MSc project, which if you're an MSc student, you're interested in doing some NLP and working with Stephanie, please get in touch.
Okay. Yeah, we'll be playing with packages like Spacey and stuff and building custom models and take a look and see if we have any, we can build our own word embedding on business technical jargon and stuff. So it should be fun.
Okay, sounds great. Okay, so thanks again. And we'll be in touch, Stephanie. Okay.